In this lesson, I'll introduce you to the chain rule. The chain rule is used when we have composite functions. Here we have a 3x plus 4 inside the cube function. We've got an x to the 6 inside the sine function. The chain rule states that the derivative of y with respect to x is the same as the derivative of y with respect to u, and then the u with respect to x. Now this seems to make sense when we consider the derivatives as small rises over small runs, and then those two du terms there will cancel out. If we cancel those out, we're left with a dy dx. I'll show you a more rigorous proof of the chain rule. If we have y as a function of some other function, so f of u of x, we can then find the derivative from its definition, and that is the value of y at x plus h minus the value of y at x, all divided by h, and we want the h to approach 0. Now what we'll do is we'll multiply all of that inside the limit by 1, written as u of x plus h minus u of x over itself. And then we can rearrange that. I'll put the u of x plus h minus u of x on the left hand term there, and the h I'll take out and put it on the right hand side there. Now we've got the limit of a product is the same as the product of each of the limits separately. And looking at the second term there, of course, that is the definition of the derivative of u. So we can write that as u dashed of x, or simply the derivative of u. So now we're left with working out that first limit. I want to put this into the form of the derivative, so I want to replace that denominator with a h. But it won't be the same as this little h here, so I'll introduce a capital H to replace that denominator. And then I can rewrite that so that u of x plus h is the subject, and that'll equal the h plus the u of x. And so then we have, as h approaches 0, the x plus h will approach x, because the h is going off to 0. And so therefore the u of x plus h will approach u of x. So therefore the h, which is the u of x plus h minus u of x, that's going to approach 0, because we'll end up with a u of x minus a u of x. And so we can rewrite that original limit in terms of our capital H here. And so firstly we'll see that the denominator is of course just that capital H, because that's how we designed it. And the u of x plus h we can replace now with the u of x plus h. And I've dropped the of x there, I've just written it as u instead of u of x. And then we have our f of u, again of x there. And we saw that as h approaches 0, then we end up with the capital H also approaching 0. So I've replaced this limit of little h approaching 0 with the capital H approaching 0. And we now recognize that to be exactly the same as the derivative of f of u. So it's the derivative of the f as a function of u. So we've got the y dx is equal to the limit of that first term that we've just been working on times the derivative of u, as we saw earlier. And so we can write that as dy dx is the derivative of f of u times the derivative of f with respect to x. And we can rewrite that as dy dx is dy du is the derivative of f with respect to u, and this is of course du dx. And the y is f of u of x, so ultimately f would be a function of x. In this example, we have a function inside the function. We have the power of 5 function, and inside we've got the function 2x cubed plus 3. So if we make that substitution that the u is 2x cubed plus 3, we then have y is u to the power of 5. And so to get the derivative, we need to differentiate the y with respect to u to get 5u to the 4, and then differentiate the u with respect to x, getting 6x squared. So applying the chain rule now, we have our dy dx is our dy du, which works out to be 5u to the 4, times our du dx, which is our 6x squared. Now the u is not really the variable we want to leave it in, so we'll replace the u with our 2x cubed plus 3. So there it is there. And then we'll just tidy it up a little bit. We won't bother expanding that power of 4. We'll leave it in factored form there, but the 6 times 5 is 30. We can certainly tidy that up. And the x squared we'll just put in front. So there's our answer. In the second example, we can see that we've got a function x squared there inside the sine function. So what we need to do is let the inside function be u, that's the x squared, and then we have y is a function of u, that is sine u. So we need to work out the derivative of y with respect to u, so that gives us cosine u, and the derivative of the u with respect to x is of course just 2x. So we can apply our chain rule there, and of course we get the dy du is cosine u, and the derivative of u with respect to x is 2x. And once again, we don't want to leave it in terms of u. We'll put the x squared again in place of u to get our answer there. And we can rearrange that and put the 2x in front. We've used the chain rule to help us differentiate a composite function where we have a function inside a function.